So in this video I'm going to be talking about orbital hybridization, which is the way that we'll explain how molecules are formed by atomic orbitals coming together and actually bonding together and not using this overly simplistic dot diagram idea. So we now understand from the last video that electrons don't exist in these nice neat circles going around the nucleus like planets go around the sun. We actually have this orbital theory, which is much more able to explain a lot of the properties that matter has and why we get things like visible light, like the light that is lighting up this room, UV light that we can't see, infrared light, lots of other different types of light and energy are caused by or help explained by orbital theory. So in the last video I talked to you about how orbitals have different shapes and then they fill up in a certain order. What I didn't tell you in the last video is the idea of electron spin. And you can think of electron spin, and the name is misleading, but that's the name that it's been given over the years. You can think of two electrons inside an orbital, like an s orbital. Don't think of them as spinning in a nice neat circle. Think of them as somersaulting, just random directions. But the other electron is doing the opposite, going the opposite way. So that helps explain how two electrons can exist in a certain orbital. They're moving in different directions, positively and negatively. So we say an electron has a positive or a negative spin. We actually showed the electron configuration of something like beryllium like this. So Be equals 2 electrons in the first energy level and then 2 electrons in the second. So the way that we'd write out the electrons would be 1s2, 2s2. So we can just add another aspect to that version and say that the electrons have different spins. Positive would be kind of this half of the arrow, and then negative would be the down version of that. So we're just trying to show that they've got opposite directions, and that's how we do it. Again, not spinning round and round like a merry-go-round, more like somersaulting randomly, but they're going in opposite ways. So the idea of electron spin is important when we start to talk about hybridization. So if we look at BeF2, which is a molecule of beryllium and 2 fluorines, how is it that this theory of orbitals and energy levels, how does that explain how this forms? Well, the ride gets a little rocky from here on in, so hold on tight. But the idea is orbitals can hybridize or mix together and form a new version, right? So what actually happens when this is being formed, and this all happens in the blink of an eye, like split second, the beryllium promotes an electron up to the 2p. To p or not to p? That is the question. Right, so it's promoted an electron to the 2p. So these electrons actually form a separate new orbital. So they aren't 2s and 2p anymore. What actually happens is that it's a hybrid of the s and the p. They kind of mix together and have the same amount of energy. So this creates two kind of unbonded electrons or lone electrons. So that might help explain how we get this F2. But we need to go a little bit further and explain something wrong. Sorry, I need to just adjust this picture. Sorry. So that's the new orbital version, is the SP combination or hybrid. So we need to go a little bit further and explain how this actually comes about. If you imagine the s orbital is a sphere, again another perfect circle, and this is our 2p orbital. Imagine them mixing together and what that would look like. So these two things have a child, and it kind of, you can think of it looking like this, right? So you've got two versions of this. So beryllium, imagine the nucleus is right here. If this represents the nucleus, you've got two versions of this hybrid orbital. So one electron, one electron. These have to be identical because these two, there's two bonds in this molecule, beryllium and fluorine bonded together, but it's happening twice. Those bonds have to be identical, so these orbitals have to be identical. Okay, and so then fluorine would have another orbital, and these orbitals would overlap and form this molecule. But the way that it happens is by the s and the p orbitals combining to make this new version, and then that creates two identical orbitals, this one and this one, so then the molecules, the orbitals can actually overlap and bond together. So the description that we have for this, and if you see that's a linear shape, we'd call that sp hybridization. Right, so the reason why it's just s and p is because you only had one of the p orbitals being hybridized. And I'll show you sp2, which involves two of the p orbitals, and then sp3, which involves 1, 2, 3. Okay. So that would be sp hybridization. So what I'll do now is show you sp2 hybridization. Similar sort of pattern. The orbitals are changing, creating this new version, and that's allowing more bonding sites. So let me just erase this. So now what we'll do is look at a different molecule. This time it's boron and 3 fluorides. So boron has the electron configuration of 2, 4, 5, so 5 electrons. So this is how these would fill up. Just a note on how this fills up, if you ignore that for a second, and let's say we had to add more electrons, how does this fill up? Well, it's actually the positive spin that fills up first. The electron with the positive spin that gets filled up first. So it'd fill up this way, and then you'd add in the negative spins. That's the way that those orbitals, fill up with electrons. So just a note about that. So we're looking at this new molecule. It's got a slightly different variation, but a similar process happens. This electron from 2s gets promoted to 2p. Then this creates like a hybrid version. So we'll just get rid of that. So whereas before we had separate s and p, now we've got this new version that has 3 electrons ready to bond with something else, and this is the boron electrons. So the way that happened, you had 2 electrons in 2p orbitals, so that's where that sp2 comes from. Basically it's saying that you take an s and then 2 of the p orbitals and hybridize them and create an sp2 hybrid orbital. So imagine that this is the s orbital, and then this time you've got, that's wrong. These are very bad diagrams, by the way. So the 2p and the 1s orbitals actually create this new version. There's an sp2 hybridized orbital. And the way that it would look, if you imagine boron is in the middle, or sorry, the nucleus of boron is in the middle, same sort of funny looking hybrid shape. So here you've created these, with these 3 electrons, you've created these 3 areas for bonding, and that's how boron trifluoride is formed. This shape would actually be a trigonal planar. So there are a lot of kind of combinations of concepts that we've talked about here. So the sp, if you see a linear molecule, it's probably sp hybridized. If you see sp2, it's probably this, or even vice versa. If you see sp2 hybridized orbitals, then it's probably trigonal planar. So then the fluorine would come along and bond here, here, and here, and you've got BF3 with these new orbital versions. And so again, this comes about from the 1s orbital, and then the 2p orbitals combine together and make an sp2. Okay, so now we'll talk about sp3. So for this example, we're going to go back to CH4, our old friend methane. So if we looked at the electron configuration of carbon, it's got 6 electrons, 2, 4, and then 6. So now, same sort of idea. One of the electrons from the 2s is going to get promoted to the 2p, so that happens first. We've all got positive spins, notice that. So now these 2 orbitals hybridize and create this new version. And how that happens is by creating this new orbital that's actually sp3. Why is it sp3? Is because you have 3 electrons in the p orbital, or you use 3 p orbitals, and then you had your 1s. Not 2s, not to be confused with 1s, this one, but just only one of the s orbitals in the second energy level. So 4 electrons, 4 bonding sites. Coincidence? No, it's not. 1, 2, 3, 4 hydrogens. So carbon, again, same sort of idea. These new orbitals are formed, sp3 hybridized. Guess what shape it's going to have? That's right, it's going to be our good old friend, the tetrahedral. I didn't draw it. Difficult to draw this in 3D, but it is in 3D. Imagine it like a tripod with one sticking up. All the bond angles would be 109.5 degrees. So yeah, this time it's sp3. It's created 4 places for bonding by combining the s and the 3p orbitals and creating this tetrahedral shape. So usually when you see an sp3 hybridized orbital, it's usually tetrahedral. Again, with chemistry, there are often exceptions to the rule, but for right now, let's just deal with the simple, straightforward ones and then deal with exceptions later on. So I'll show you another example of this. But if ever you see carbon with 4 things around it, you already know pretty much it's going to be tetrahedral. Whether it's polar or not, you don't know until you actually examine each bond individually. But if it's got 4 things around it, so CH4, or it could be CH, and then 3 chlorines, right? It's going to do this kind of hybridization, and it's going to form this kind of shape. So there's some patterns, and there's some easy ways to remember those things. So I'll show you another example of sp3 with our good old friend H2O. I'll go through the same steps all over again. B2S. So we're looking at H2O. So in every case so far, we've looked at the central atom, and usually the central atom is just the one atom in a molecule. So CH4 carbon, there's only one of those, it's the central atom. This time it'd be oxygen, there's only one of those, right? So oxygen is in group 8, and it's, group 6, 8 electrons. So 2, 4, 5, 6, 7, 8. Okay, so slightly different version here with H2O. But similar sort of process. You actually get the same promotion of an electron from the 2s up to the 2p. So that happens first. Then these two orbitals form a hybrid. It's easiest just to erase the whole thing. These are all supposed to be the same size. So we had 2. So again, it's sp3 because we used 3 p orbitals and then 1s to combine to make this new version. This time though, you've got 2 pairs of electrons here and only 2 free electrons for bonding. So oxygen actually has 2 lone pairs of electrons. So remember from drawing these kinds of shapes, oxygen has 2 bonded pairs, 2 lone pairs. So these are the lone pairs, and these are the bonded, or will be the bonded pairs when they bond with the 2 hydrogens. So same sort of idea. This time though, if you imagine oxygen's in the middle, hydrogen could combine here with its orbital, and then oxygen's lone pairs just exist that way. So it's still sp3, even though you've only got 2 bonded, or will have 2 bonded pairs of electrons, still sp3. So, just to recap, the whole idea of orbital hybridization is helping explain how even if you have electrons in an s orbital, that is a different size and shape than the 2p orbital. So then that would perhaps suggest that the bonding would be different, but the bonding isn't different. H2O, the oxygen-hydrogen bond is identical in both cases. There's ways to experiment and actually prove that. So that there's got to be some kind of explanation for how the bonds are the same, even though the electrons might come from different orbitals. And the explanation is hybridization, so S and p orbitals coming together and creating a new version, and that's allowing us to explain how this happens. So, and that also explains molecular orbital theory, which is kind of, it's orbital hybridization, the two ways to say the same thing. Phew, that was fun.